All right, today we're diving into something really cool. It's a new framework called HEAS, which stands for Hierarchical Evolutionary Agent Simulation. And it's designed to give scientists a seriously powerful new way to model and understand the incredibly complex systems that are all around us. So let's just start with a question that scientists have been wrestling with forever. How do you even begin to build a computer model of an entire ecosystem? The thing is, it's not just about modeling one thing at a time. You've got individual animals making their own choices, right? But they also exist inside of groups, which have their own behaviors. And the whole shebang is happening inside an environment that's constantly changing and influencing everything, the individuals, the groups, all at once. Trying to capture all of that is, well, it's the holy grail of this kind of science. Now, to deal with all this complexity, researchers have had to get pretty scrappy. But that's led to let's call it a messy problem. It's something the creators of HEAS called the glue code mess. See, to get this work done, scientists often have to cobble together a bunch of totally separate tools. They'll use one program to build the simulation itself, like NetLogo. Then they'll need another specialized library to optimize the strategies for their agents. And then they need even more tools just to compare the results. The problem? To make all these different pieces of software actually talk to each other, they end up writing tons of custom, messy, and super error-prone code. That's the glue code. It slows research to a crawl and makes experiments almost impossible to reproduce. So, what's the fix for all this digital plumbing and patching? Well, this is where HEAS comes in, and it offers a much more elegant solution. HEAS is a single Python framework that brilliantly takes all those separate, clunky pieces and combines them into one seamless toolkit. It actually unifies the simulation, the optimization, and the evaluation into one clean, repeatable workflow. In other words, goodbye messy glue code. Okay, so how does it actually manage all this complexity under one roof? The best way to think about it is like a perfectly organized assembly line, but instead of building cars, it's building scientific insights. The most basic building block on this assembly line is called a stream. A stream is just a tiny little process that does one specific job and does it well. Maybe it's calculating how the weather changes, or it's running the decision-making logic for a single agent. It's just one specialized worker on the line. Then you take these individual workers, these streams, and you organize them into layers. So for every single step or tick of the simulation, layer 1 runs first. Let's say that's the environment update. Then layer 2 kicks in, and all the agents read that new environment state and make their moves. And finally, layer 3 might run to scoop up all the data and calculate the results. It's a clear, predictable, step-by-step process. But how do all these different layers and workers communicate with each other? This is the really clever part. They use something called the shared context. Just picture a giant whiteboard in the middle of the factory floor. Every stream can walk up to that whiteboard, read the current state of the entire system, do its own little job, and then write its updates back on the board for the next stream in line to see. It makes everything explicit and super easy to track. Now, this incredibly clean architecture is what gives the HEAS framework what I like to call its 3 superpowers. It gives researchers 3 core capabilities right out of the box. First, you can just simulate. You can run your model forward in time to see what happens, see how it behaves, just like any traditional simulation. Simple and effective. Second, and this is where it gets really fun, you can optimize. HEAS has powerful evolutionary algorithms baked right in. That means you can literally tell it, hey, go find the best possible strategies for my agents to achieve this goal. And it will automatically search for and discover them for you. And third, you can evaluate. This one is awesome. It lets you set up these tournaments where different strategies and policies can compete against each other across a whole range of scenarios, so you can see which one is actually the most robust and performs the best overall. Okay, so this all sounds fantastic in theory, right? But where does the rubber meet the road? Well, the creators put HEAS to the test in 2 completely different and really complex fields. I mean, check this out. On one hand, they applied it to ecology, modeling that complex dance between prey and predators to find the best survival strategies. But then they used the exact same framework to model business systems, with competing firms, government regulators, and market signals, all to discover the most profitable business strategies. The versatility here is just incredible.
Let's zoom in on that enterprise example because the results are pretty stunning. They started with a standard baseline business strategy, what they call the reference policy. Then they unleashed HEAS's optimization engine to evolve a brand new champion strategy. So, look at these numbers. The standard policy, it pulled in an average profit of about 375. The champion policy that HEAS evolved, over 1,000. That is an increase of over 660 units. I mean, to put that into perspective, HEAS didn't just find a slightly better way of doing things, it discovered a fundamentally superior strategy that almost tripled the average profit across 32 different market scenarios. That's not an improvement, that's a breakthrough. So, what's the big deal here? What does a tool like this really mean for the future of science? Why does it matter so much? I think this quote from the researchers themselves just sums it up perfectly. By handling all the messy connections, by getting rid of that glue code, HEAS allows scientists to stop spending all their time on plumbing, on just trying to get the pipes to connect, and instead focus their effort on inquiry. It frees them up to ask the bigger, deeper, and more important questions about our world. And that really leads us to the final and maybe most exciting thought. With tools that make modeling these incredibly complex, multi-level systems so much easier and more powerful, you really have to wonder, what new secrets about our world, from how forests grow to how economies function, are we now on the verge of unlocking?